Great. So, hi everyone. Yes, Suman last week asked me to give a talk about line intensity mapping and other things to open your eyes to all in the universe that is not 21 centimeter. So that's what I want to do. So, just to start, so we have this picture of the cosmic history of the universe. We've got a cosmic microwave background at very early times. We have galaxy surveys at low redshift. And broadly speaking, our goal is to understand all of the stuff back in here, both because we want to do cosmology and learn about fundamental physics, and also to understand astrophysics and galaxy formation and all of the very messy things that Mark was telling us about in his talk. And so that's where the kind of 21 centimeter at the epoch of reionization that I think you heard a lot about at the beginning of this week, and line intensity mapping kind of fit in. So this is a picture of a traditional large galaxy survey. So this is with DESI. So there's about 600,000 galaxies in this. Every point is a galaxy, and you can see the kind of filaments and voids of the cosmic structure shaped out there. And in order to build a galaxy survey like this, you need, with your telescope, to identify individual galaxies, both in angle and ideally in redshift. So getting redshift information on galaxies is hard. You can do it with colors and photometric redshifts, and those tend to be quite inaccurate. Or you can do them with the spectra if you want to position something very well in redshift. And that's expensive. It takes a lot of time, telescope time, people time, and money to do a spectroscopic survey like this. And that's a bit of a pain because if you want to do cosmology, then often you don't care about every individual galaxy. You care about, in some sort of averaged way, how is the density distributed? And so you'll take these individual galaxies and in a crude way, bin them up to get the overdensity in different regions with which you can do statistics and measure things like the baryon acoustic oscillation feature in the galaxy correlation function. So you might have seen DESI with these measurements of the BAO at many different redshifts recently suggested that there was evidence for an evolving dark energy equation of state. So this is very important cosmology that we'd like to be able to do. So we'd like to get large galaxy surveys like this as efficiently as possible to do this kind of cosmology. And that's where the idea of intensity mapping kind of arose. So the goal here is to get very quick, efficient, spectroscopic maps of the galaxy distribution. And just to give you a sense of what that looks like. So this is from a numerical simulation, all of the galaxies in that simulation. This is the brightest galaxies there, which are the kind of galaxies that we tend to see in our surveys. The faint population's just too faint to see. And this is a map of the intensity in the carbon monoxide 1 to 0 line. And so the idea here is that you point your telescope at some region, it's got some beam, it doesn't resolve the individual galaxies, but it integrates up all of the flux from all of the galaxies in this line in that region. And so that will tell us about overdense regions and underdense regions in, hopefully, a fairly straightforward way. And you're losing some information about the smallest scales, but very often we don't really care about that for cosmology. And you're gaining something because this is sensitive to the very faint galaxies, which you're not seeing with the traditional galaxy survey. So that's the kind of the dream. And so you can use it for cosmology to map large volumes in order to get high statistical sensitivity. But you can also use this for astrophysics. So Mark was telling us a lot about the evolution of H1 over time, the evolution of molecular gas over time. And as he said, it's very difficult at the moment to detect galaxies at above redshift of 0.5 in hydrogen. And so intensity mapping is maybe a way of doing that to higher redshift. And so you can probe the full galaxy population and measure the star formation history, maybe, measure properties of the interstellar medium, especially the abundances of metals and molecules inside of galaxies, their kind of ionization states. You could learn about reionization. So this is going to be quite complementary to the kind of 21 centimeter studies you heard about earlier. Yeah, in the faint population. So there's maybe a lot of interesting things that you could learn about if you care about astrophysics. And so the question I kind of want to address in this talk is, well, okay, so how do we do this intensity mapping? So we need to identify individual lines that we can use, like the 21 centimeter, but other atomic and molecular lines. We need some way of modeling the emission from those galaxies so we can make predictions for what our telescopes will see. We need some sense of the kind of telescopes that will detect this. So I guess you've been sweating through radio interferometry, and that's hard, but really exciting. But for this, we'll need slightly different telescopes maybe. And then sort of connect this to the cosmology, understand what we can do if we measure things. And so the goal is, again, just to fill in this space between the CMB and galaxy surveys with line intensity mapping surveys. Okay, so we'll talk about a bunch of different lines, but to start off, I wanted to talk about the 21 centimeter line, because that's the one that you're probably already very familiar with. So this is our friendly spin flip line of neutral hydrogen, and these are just some maps that I'll say a bit more about in a moment. So the nice thing about the 21 centimeter line, so it's 21 centimeter, 1.4 gigahertz, and it's very well separated from any other atomic transition. So those tend to be more millimeters or micrometer wavelengths. And that means if you see a 21 centimeter line, you kind of know it's a 21 centimeter line, tilde. So when you talk about the epoch of reionization 21 centimeter signal, that's coming from the neutral hydrogen in the space between galaxies. I think you'll have seen in the numerical simulations how ionized photons, ionized bubbles around the galaxies. And so you're not seeing that region where the galaxies are, you're seeing the gas far away from that. So now we want to segue to thinking about the 21 centimeter signal after reionization is complete. So all of that neutral hydrogen in an intergalactic medium has been ionized. And what we're left with is neutral hydrogen inside of galaxies where the recombination rate exceeds the ionization rate, and we can get neutral hydrogen regions. So this is neutral hydrogen inside of the galaxy. So we can calculate the kind of average brightness temperature, so the measure of the intensity in this low frequency regime. It depends upon a bit of cosmology, but mostly it depends upon this parameter omega h1. And so that's the fraction of the critical density present in neutral hydrogen. We don't know it very well. So this is it's a slightly old plot now, measurements of omega h1 as a function of redshift from a mix of radio surveys, optical surveys. You can see there are large error bars all over this. This is the kind of simple model. But broadly speaking, the amplitude of this is about 10 to the minus 3. So we've got some sense, a clear sense of how much neutral hydrogen there is, and so the kind of signal that we're looking for. Okay, so there's a small signal. As with the epoch of reionization, 21 centimeter, there are large foregrounds. So there's radio emission from our galaxy and synchrotron, free, and so on. That tends to be very smooth spectrally compared to our fluctuating 21 centimeter signal. And so the hope, as with the EOR, is that you can remove those smooth foregrounds with some kind of simple, smooth polynomial fitting, or things like PCA or Gaussian process regression and so on. So you can remove those. And this is just an illustration of that. So this is a map that was made with the Meerkat telescope in South Africa. It is only about 11 hours of data targeting a redshift of 0.5. And so you can see there's lots of stuff here. This is all foregrounds. If you fit 30 PCA components, and that's a large number, then you can get to this cleaned map where you can see something that maybe starts to look a bit more like a Gaussian random field, although there's still bits of crud in there. And so at the moment, this kind of expensive fitting is part of the problem for these intensity mapping experiments. There's a need for better calibration of instruments and all of these sort of things. But in principle, you can do this. Okay, so you remove the foregrounds, you have fluctuations, and the way we normally describe fluctuations is with a power spectrum. And so for the H1 power spectrum, that will be proportional to just the linear matter power spectrum. And so that has information about cosmology in it. There'll be some overall multiplication by the mean brightness temperature. So that will depend upon the omega H1. There'll be some bias associated with the biasing of galaxies versus the linear density field, some redshift space distortions, which we won't really touch upon. So this is the kind of power spectrum that we want to measure. The amplitude of that has a bit of a degeneracy. So omega H1 appears in TB, there's a bias, and so you measure this kind of a parameter combination here. But that has useful information in it. And to some extent, you can break that degeneracy with the redshift space distortions. And if you're modeling this, this starts to get into the kind of messy nonlinear phase where you need to account for nonlinear growth in your power spectrum. But anyway, so in that power spectrum, you'll see features like the baryon acoustic oscillations. So these are just some plots of the power spectrum with the overall broadband shape fitted out. And you can see these oscillations here, which have the same physical origin as the acoustic peaks in the cosmic microwave background. And so the valuable thing about these is that they're essentially a standard ruler for measuring cosmology. So if you measure the angular size of these, we know the intrinsic kind of size from the CMB, and so we can measure the growth of the universe and so probe things like the dark energy. And so I mentioned the DESI result at the moment with maybe an evolving equation of state for dark energy. 21 centimeter intensity mapping could do exactly the same sort of thing. So you have a clustering power spectrum. There's also something known as shot noise that comes into effect here. So individual galaxies are discrete objects. And so if you look at a region of space, there'll be some counting error on that. It's a Poisson statistics of how many of those discrete objects are from place to place. So typically that looks like 1 over the mean number density of galaxies. But with H1, you need to reweight that because we care about the mass rather than the number. So things get a bit more complicated. And so generally, the total power spectrum that we measure is going to be a sum of a clustering kind of cosmological bit and a shot noise bit associated with the details of the individual objects. And it looks something a bit like this. So on small scales or large K, you tend to be dominated by the shot noise. And on large scales, small k, you're dominated by the clustering. So there's these kind of two phases, two regimes for the power spectrum that we can measure. Okay, so then you go away and you look at your radio telescope and you try to measure this. And so you've been learning a lot about interferometers, I imagine. So with the EOR, we work with these antenna and stations. And so you tend to work in this interferometric mode. For 21 centimeter intensity mapping, you tend to work with dish telescopes like Meerkat. And there you've got two options. You can do interferometry between the individual dishes, or you can just point your dishes and measure the total power and work in what's known as a single dish mode. And so there are pros and cons to both of those. The important thing here is that the interferometric mode, because you're combining widely spaced baselines, it tends to probe smaller angular scales on the sky. So that's these kind of larger K-perpendicular modes. The single dish tends to be good for probing the large modes on the sky. And so you've got these two different modes. And as you translate a given co-moving scale on the sky, like this baryon acoustic peak, sometimes it would be better to use your telescope as an interferometer to detect that, sometimes in a single dish mode. So in general, the interferometer will see these kind of smaller, large modes. A bit weird. So to help visualize that, these are some of the experiments that are trying to do 21 centimeter intensity mapping at the moment. So Meerkat is in South Africa, and that's on the site of the SKA mid. And SKA mid will essentially just swallow Meerkat and add extra dishes like this. This is Chime in Canada, and you see it's got this cylinder-shaped dish design. In China, there's an experiment called Tianlao, which is experimenting with both of those designs. In South Africa, there's a project starting Hirax with lots of dishes. DSA 2000, GMRT is trying to do this. Lots of different experiments. So, but you see there's lots of these kind of dish interferometers. Okay, so you build these telescopes, you try to measure this 21 centimeter intensity fluctuations. What kind of things can you do with that? So as I say, there's these two kind of modes. So the interferometric mode tends to be focused more towards the small scale. So you tend to see more of the kind of the shot noise, and through that you can probe the distribution of H1 inside of kind of galaxies. You don't see the galaxies, but you learn something about H1 distribution relative to that. So here we go with some Meerkat surveys and SKA at redshift 0.1. These are the kind of sensitivity bands. They're probing the kind of shot noise bit. As you go to higher redshift, you start to get more of the kind of clustering signal. If you could push that to redshift 3 or so, then the interferometer would be able to start to do BAO kind of stuff, dark energy. That's, maybe less exciting, I think, for many people, but very valuable for learning about the H1 distribution. For the kind of single dish mode, that's really where you want to go for a lot of the cosmology. So with Meerkat targeting kind of a redshift of 0.5, then you begin to be able to do the kind of BAO measurements. And with SKA mid, you'd be able to do quite competitively compared to the kind of big spectroscopic galaxy surveys. So this is just from a sort of an old paper showing the kind of predictions that people have for facility here is kind of SKA, stage 2 is kind of the Meerkat and Chime, Dark Energy Task Force 4 is the sort of big spectroscopic galaxy surveys. And so with SKA, you're kind of competitive with that. And one of the valuable things there is that intensity mapping has very different systematics to the kind of traditional galaxy surveys. And so if you're worried that you're making mistakes in the analysis of one of those, you could combine those with the other and hope to remove some of those kind of systematic effects. So it's very valuable to observe the same thing from radically different directions. Unfortunately, we haven't done that yet. So as with 21 centimeter in the epoch of reionization, there's a lot of effort going on in order to try and detect these signals, but we haven't got there just yet. So a couple of years ago, there was the first detection with Meerkat of the H1 intensity in the interferometric mode. And so these are just some error bars that they have on their power spectrum. You can see this is quite low redshift. So this is redshift of 0.3, redshift of 0.4. You can compare that to the Chile's detection at redshift of 0.4 that Mark was mentioning. So this is sort of comparable to that. These are on the kind of small scales, probing that turnover from the shot noise into the clustering sort of a signal. In the single dish mode, there hasn't been a detection yet. And so this is the challenge of making an autocorrelation detection. You really need to understand your instrument very well, remove the foregrounds very well, all of the same kind of problems that come up for the epoch of reionization experiment. What you can do is to cross-correlate the 21 centimeter intensity maps with optical galaxy maps. And so the advantage there is that the optical galaxies they're only the brightest galaxies, but they tell you where you expect to find clusters of galaxies. And so those are the regions where you expect there to be more hydrogen. And so you expect that wherever you get more hydrogen, you'll get a stronger intensity mapping signal, and that will connect to the overdensities in the galaxies. And so if you cross-correlate those together, the galaxies are pointing the way to where your intensity mapping signal should be. And so this top panel here is a cross-correlation between Meerkat intensity mapping and the Wiggle-Z galaxy survey. And you can see there that there's a fairly convincing detection of something. And so with these cross-correlations now, especially in the last couple of years, both Chime and Meerkat have been able to see this 21 centimeter intensity mapping signal. So we know that it's there. We just haven't yet got to the point of analyzing things well enough to get the autocorrelation. Okay, so that's my sort of lead into 21 centimeter intensity mapping. So it's very exciting at the moment because for the first time, we're starting to get observations of this signal in the interferometric mode, in the autocorrelation, in the cross-correlation between single dish modes and galaxies, not yet the single dish autocorrelation mode. And as these experiments get better understood and as there's more sensitivity, some of the sort of science that we'll be able to do are things like pinning down that post-reionization H1 fraction, so getting error bars that look like these little black ones rather than these kind of messy ones, measuring the dark energy by mapping out the baryon acoustic oscillations, and potentially going to very large volumes and looking for the kind of interesting cosmology that you can get there from modifications to gravity or inflation. And maybe eventually being able to do things like constraining neutrino masses. So, there's a lot of potential in the future with SKA experiments like HIRAX, which are all sort of coming in the not too distant future. So the 21 centimeter line is great, but it's really not the only line in town. So it's worth us thinking about other atomic and molecular lines that one could look at. So these are two galaxy spectra. So this is M82, which is a relatively nearby galaxy. You can see there's this kind of hump there of continuum emission, and then a whole bunch of different lines. So that's maybe what a low redshift galaxy looks like. And then this is a simulation of a lot higher redshift galaxy. Again, you've got lots of lines. There's some continuum emission. And so everything that you do with 21 centimeter intensity mapping, you could potentially do with any one of these lines. And so it's worth exploring which of these are valuable for intensity mapping and how much you can learn from it. And I'll plug this. This is a very nice review article on line intensity mapping, which I've borrowed from shamelessly in this talk. So I recommend going to read that if you have any interest in these. So there's lots of different lines, and we can kind of break that down into like a long list of possible lines that one could look at, or a slightly more visual version of that. So some things to point out. So we've got carbon monoxide lines. So carbon monoxide, it's a little molecule, it rotates. There are rotational transitions between different angular momentum states J. And so you get this ladder of different lines with wavelengths given by this kind of a formula. So those are nice because the spacing between those is very regular, very, very well understood. And carbon monoxide is a very common molecule. Another one to pick out is C2 here. So C2 is one of the brighter lines in galaxies as we go to high redshift. But there's also oxygen, nitrogen. There's some other ones as well, but we tend not to worry too much about those. Okay, so let's imagine that we take one of these lines, and so these have wavelengths that are somewhere around 100 or so micrometers. And then we try to look at that at higher redshift. So the frequency that we observe things at will look like the emitted frequency divided by 1 plus redshift. And so if we're looking at some fixed frequency band, then different lines at different frequencies will probe different redshifts. So this is just illustrating that. So here are some of the CO lines with their observed frequency as a function of redshift, and you can see that as we go to higher redshift, they fall at lower frequency, and there's C2. So that's good. So if we can identify a line at 260, we could identify C2, and we would know that it was a redshift of 7 and a bit. And one thing for this to remember is that from the Earth, we don't have freedom to look at any wavelengths we like. The atmosphere absorbs a lot of wavelengths, and so we can only play within particular atmospheric windows, which is why these kind of hundreds of gigahertz is quite a convenient one. This is kind of millimeter type wavelengths, millimeter and submillimeter type tasks. Okay, so that's good. So if we can find a line at, say, I don't know, 260 gigahertz, then we can know the redshift. Life would be easy, except that if I come across at a fixed frequency, there's a bunch of different lines that all contribute at the same point. So the total, when we make an intensity map, the total intensity that we see will be the sum of the intensity from all of the different lines that contribute to that frequency. So for example, if we looked at 317 gigahertz, we could have some carbon 4 to 3 emission from galaxies at redshift 0.45. That falls around there. We could have carbon 6 to 5 at redshift from galaxies at redshift 1.2. Same thing. Carbon 2 at redshift 5. That also falls around the same thing. So these are just examples of 3 different maps with different structures in 3 different lines. And if we observe a frequency of 317, we'll see the sum of all of these. Okay, so that's going to be a bit of a problem. So in an ideal world, that's not a problem because one of these is much brighter than the other ones, and that's the one that you want to look at. And then maybe you can ignore the other ones. That seems far too easy, doesn't it? And so if we are looking at high redshift ones, that will tend to be the faintest one. And so we'll need a way of disentangling it from these other lines in order to pick that one out. But that's something that we can imagine doing. So we can imagine having maps at different frequencies and kind of cross-matching them to pick out the emission from galaxies at some target redshift. So let's say we've got galaxies at redshift 6. We know they emit in an oxygen 63 micron line and an oxygen 3 52 micron line. Okay. And then those wavelengths redshift to today, to these ones. So if we've got maps at this and this, and we compare them, then you can see in here there's some red dots. Those are the redshift 6 galaxies. The blue dots are galaxies at other redshifts that have some sort of a line that falls at this wavelength. And it looks a bit like finding a needle in a haystack, doesn't it? And the same over here. But if you compare these two, then these red dots are the only, well, essentially the only ones that are common between the 2 maps. And so by cross-correlating them, you can pick out the handful of galaxies that correspond to redshift of 6. And so this is a technique that's often used for identifying lines in individual galaxies, and we can apply it to these kind of intensity mapping surveys as well. Okay, so I've mentioned a couple of key lines. So we've got 21 centimeter, which is neutral hydrogen, CO, which is a very common molecule. It's second only to molecular hydrogen, and so it's very important for cooling of gas. And there's an argument that carbon monoxide will often be linked to the amount of molecular hydrogen, which in turn will be linked to the amount of star formation rate. So this is a good tracer of the star formation rate. Life is complicated. It's not quite as simple as that, but this is the sort of story you can tell. Things like carbon-2 probes photodissociation regions in the molecular clouds, but it's also probably a good tracer of the amount of atomic gas in galaxies and the star formation rate. And other lines that you could use to probe the interstellar medium and what's going on there, or things like H-alpha, H-beta, which are recombination lines of hydrogen, which will tell you very directly about star formation. Lots of different possibilities with different science cases associated with them. Okay, so we've worked out there's a bunch of different lines that we could look at, and now we need to understand a little bit how we can model a signal. So we want to go from some kind of galaxy distribution to some kind of intensity field to some kind of power spectrum that we can then try to observe. So this isn't easy. So it's great that I followed Mark's talk because he talked a lot about all of the messy physics that goes into individual galaxies. So you have galaxies, there's flows of material out of them into the, what do you call that? The CGM? Yeah, circumgalactic medium, that's right. Gas gets blown out, gas comes back in, you have cooling of gas to form molecules, you have shocks that can break that up or condense things. There's a lot of structure and physics within here, and different molecular gas will live in different places, either closer into the center or maybe more in the outskirts. And so to model this from first principles is quite a demanding enterprise. And so that leads to a lot of uncertainty in the kind of model predictions for intensity mapping experiments. But the kind of strategy that we can use is pretty straightforward. So first we want to model the kind of the mean intensity. And then once we've got a sense of that kind of mean signal, we can model fluctuations within it that will give us our power spectrum. So the thing that we're trying to measure is an intensity. So this is going to be some specific intensity per unit frequency or in a particular line. And you can write it in terms of the luminosity density, so the kind of energy per second being radiated from within some volume, just by multiplying by CE each other factors here. So this kind of mean luminosity density is the key quantity we want to be able to model. And we can do that. So this intensity mapping signal is coming from galaxies. So it makes sense to base our model on what we know about galaxies. And when we try to model galaxies, we tend to first model dark matter halos, which are easier to understand. And so this mean luminosity density looks like some integral over the number density of the dark matter halos. And so that's something that we can predict with reasonable confidence from cosmology or from our kind of n-body simulations. Then for every dark matter halo, we need to assign some luminosity in our line. And that needs to depend upon the mass. It will probably depend upon the redshift. This is where a lot of the uncertainties in our modeling are going to come into play. And then if we integrate all of those, over all of those, we'll get our mean luminosity density. So how do we assign some kind of luminosity to a mass? There's lots of different ways, but a kind of generic construction is first to assign some star formation rate to those halos. So you could do that in a simple analytic way. So you've got some mass, there's some amount of baryonic gas in there, and on some time scale that gets converted into stars. Or you could go away and you could fit to observations of galaxies with some sort of power laws or to numerical simulations. But you've got some prescription that gives you a star formation rate as a function of mass. Then you need to connect that to emission. And a fairly standard way is to go through an intermediate step of connecting the star formation rate to the infrared luminosity. That's something that's easier to measure and is reasonably well calibrated. And then you can go away and look at lots of galaxies and find empirical correlations between infrared luminosity and the luminosity in your line. And if you can measure this at low redshift, maybe it also holds at high redshift. And so you can extrapolate, and that will give you a prescription. At each step in this, there are different choices you could make. And so you end up with lots of different, lots of uncertainty in the different models. And I'll show that in a little bit. But if you fold all of this together, then you get predictions that look something like this. So here's a star formation history as a function of redshift. And you see it's got this characteristic Medal form. It rises to a peak somewhere around redshift 2 at cosmic noon, and then falls as you go to higher redshift. And the mean intensity in these different lines looks fairly similar. It's not surprising that it's also peaked somewhere around redshift 2. That's where most of the star formation rate is. But it will be weighted somewhat differently because lower masses may emit more than higher mass galaxies and so on. So this is the sort of the general form. And some things to take away from this. So if we want to observe around cosmic noon, that's great. That's when these emission is the highest. If we want to observe at higher redshift, then the emission there is going to be fainter than at lower redshifts. And so we're going to have to work harder to deal with interloper lines. So that's a bit of a pain. But hey-ho. Okay, so I said that there are different approaches. And I mentioned empirical scaling. We can calibrate on low redshift galaxies and just extrapolate wildly. We could do some complicated modeling of the physics of the gas. And we probably need to account for just galaxy to galaxy scatter as well. And you can end up with very big differences. So this is a comparison of the mean intensity in the carbon monoxide line from a number of different groups. And you can see there's about 2 orders of magnitude of variation between the different models. So you might say, well, that's bad. We don't really know what we're predicting. And I might say, that's really good, because if we measure this, then we've learned a lot. So, you know, potato, potato, as they say. But this means that there are challenges in predicting exactly what experiment we'll see, exactly what in the future. Okay, so we've got the mean signal, and then we want to understand fluctuations. And that's generally relatively straightforward to do. So once we've got a prescription for the individual galaxies, we can put them into some framework that tells us about statistical fluctuations. So analytically, that might be something like the halo model. So you have your individual halos, you could have a prescription for the, making the power spectrum out of that. Or you can go to a numerical simulation and just paint the individual dark matter halos or maybe cells with whatever the line emission from your model tells you. And so this is an example of that. So this is an n-body simulation at sort of redshift 2 to 3. And then here we've painted, or they, sorry, have painted carbon monoxide emission onto all of the cells, and you get a nice intensity map. Okay, so then you can, well, you know, think a little bit more broadly about all of the ingredients that go into that. So this is just a kind of a summary of a code called limfast, which I just wanted to show because it gives a feel for all the ingredients that you need to bring in, especially if you want to do intensity mapping during the epoch of reionization. So limfast is built on 21 centimeter fast. And that basically is doing your density field, your halo mass function, and getting you your ionization field. And then on top of that, you're adding a prescription for the star formation rate, metallicity evolution, gas mass in all your halos. You need a prescription for what the molecules inside of the interstellar medium look like, and then a prescription for how that ISM emits. And then once you've got all of that together, you can combine all of this astrophysics with all of this to get your line intensity mapping signal in your ionization field. So it's not necessarily horribly complicated, but there's a lot of different elements that need some sort of a prescription for. Okay, so once you do all of that, you can make predictions for a power spectrum. So it has exactly the same sort of form as we saw for the 21 centimeter intensity mapping. There's going to be some term that has to do with clustering and some term that has to do with shot noise. And again, the shot noise will dominate on the smaller scales, clustering on the larger scales. These terms just look a bit more complicated here because of how I've drawn them, but yeah, and you know, as for 21 centimeter intensity mapping, to some sense, the clustering is where the cosmology comes in. So because this linear power spectrum is where cosmological parameters are kind of most interesting, BAO lives there, shot noise for studying galaxies. Okay, so you can look at different traces of the density field. And once you've got more than one tracer of the density field, then it's very interesting to start cross-correlating them all together. And so the reason for that, you know, so here, let's say I've got field A and field B. And for each of those fields, there's some signal, but there's some noise added to it, and there's some contamination from foregrounds. And so if you cross-correlate the two of those, you've got a lot of nasty terms here, potentially. And if you were cross-correlating A with A, you'd have to worry about all of these terms. But if A and B, well, if they're with different instruments, for example, the noise will be uncorrelated. The foregrounds will be very different at different frequencies. And so most of these terms will drop out, leaving you with just the signal. So the hope is that by cross-correlating two different traces together, you can get a much cleaner probe of the signal that you're looking for and reduce the problems with the in-wing foregrounds. There's kind of three main traces that you can look at. So you could take your line intensity mapping and cross-correlate it with a galaxy survey. So that's good. The galaxies tell you where the gas should be. You can cross-correlate two different lines together. So that's the sort of cross-matching that I described earlier, where we pick two lines so that we can target galaxies of a fixed redshift and use this as a way to remove all of the kind of interloper lines to target that. Or you can do intensity mapping with the kind of epoch of reionization 21 centimeter signal. And that's particularly nice because that's where you see interesting anti-correlations. So this is my kind of cartoon. So here's galaxies. If you smear over the galaxies with a beam, you get your intensity map. If you do complicated ray tracing and whatever, you get a 21 centimeter ionization field. So wherever there are lots of galaxies, sort of here, you expect to get lots of intensity mapping. So intensity maps and galaxies are correlated with one another. But with the EOR, the galaxies ionize the hydrogen, and so you get holes. And so those holes are anti-correlated with the bright spots of the intensity maps. And one of the kind of holy grails for EOR 21 centimeter is to have an intensity map like this that you can cross-correlate with your 21 centimeter signal and see these holes and bright patches line up and give you a very robust detection of the 21 centimeter signal. So for that, you need intensity maps at redshifts of 7, 8 or so. Yes, and as I said, so I mentioned this idea of interlopers before, and I just wanted to show the power spectrum for that. So again, this total one, the total one looks like this. That's great if you want to look for this low redshift CO, but if you're interested in the high redshift C2, that's buried underneath all of the low redshift CO. And so that's where this kind of cross-correlation might be really useful to pick out your kind of CO. And once you start cross-correlating two things together, you can run wild with other things that you can cross-correlate with your signal. So if the intensity mapping is tracing the density, then so do other things. So there's the kinetic Sunyaev-Zeldovich effect, where CMB photons scatter off moving ionized clusters, and maybe there's a cross-correlation there. There's lensing, and so there's a cross-correlation there. There's, well, everyone likes to do gravitational waves at the moment, and so wherever there are galaxies, there'll be merging black holes, and so maybe there are cross-correlations there too. You know, why not try it if you've got the data set? Okay, so hopefully you believe me, there's an interesting signal to be detected. And so the question then is, well, can we actually detect them? And if so, how? And I'll come back to this figure in a moment. So this is just some nice pictures of different telescopes that are trying to detect the intensity mapping signal. So many of them, their names are things like Time or Concerto. And that's really the name of the sort of instrument package that lives on a telescope, like this is I think the Arizona Radio Observatory. This is the Atacama Plateau Explorer, I think. So things like that. Or you can build purpose-made experiments like COMAP, CCAT. These are, well, the names give it away. That's a CO experiment, another CO experiment. Does a mix of things. You can go into balloons to get high in the atmosphere. You can go into space, and Sphere X launched early this year. Or you can do things like Lyman alpha and H alpha from the ground. And this is HET-X. I can never remember the name of the telescope. It's the same as SALT, but anyway. So where do we stand? So unfortunately, it's the same kind of picture as with everything, but these are very early days. And so we don't yet have really convincing detections of things. So where people have sort of tried to do intensity mapping initially was to look back at archival data and try and find carbon monoxide intensity fluctuations in that archival data. So the cosmic microwave background experiments observe at exactly the right kind of frequencies to detect CO at low redshifts. So there's been a lot of interesting work with people going back to look at WMAP data, Planck data. This is the Sunyaev-Zeldovich array. These are all kind of CMB experiments. And then possibly by cross-correlating with galaxies to try to pull out the CO intensity mapping from that. And also by kind of stacking Lyman alpha signals. And so there, a number of these have succeeded at getting low sigma, like kind of 8 sigma detections of the intensity mapping signal, which is good. It proves it's there. We're not just completely crazy to go out and look at this, but it's a far cry from where we would like to get to. So this just, visually, these are very large error bars, upper limits. and what you really want are nice clean detections. Okay, so just to give you a bit of a summary of the kind of instrumental landscape. So there are lots of different lines. These are the main ones that people target, especially these kind of experiments to look at CO at low redshift or C2 at high redshift. For Lyman alpha, if you want to go to high redshift, you need to be in space like Sphere X. From the ground, you can only look at low redshift. So this kind of summarizes that redshift dependence. So you see HET-DEX looking at low redshift. I'm colorblind, so this is a terrible figure for me. Either H alpha or Lyman alpha, I can't tell which. Sphere X, all of those at all redshifts. You have CO map and COPS at CO at low redshift and kind of high redshift. So that's important to understand. Very important is the kind of area that these telescopes are looking at. So some experiments are quite small fields. So this is a 1/100th of a square degree. So that's interesting, but it's not great if you want to correlate it with large galaxy surveys. A lot of these are trying to do kind of 100-degree, 400-degree fields. That gets much more interesting for cross correlations with, say, 21 centimeter E in the EOR. And then things like Sphere X, which is a space mission surveying over the whole sky. Sorry, I've got a cramp in my foot, so I'm just going to take my sandal off. Right, so I wanted to show you a nice picture of an instrument, just to give you a bit of a feel for that. So this is CO map. So this is a 10-meter dish. And under that dish, you have things like this. So these are 19 photons for 19 pixels. You've got some cryogenically cooled electronics for making the detection. And they've run a Pathfinder experiment, and they've got a plan for an extension. So what you can see here is that they've got, at the moment, this one frequency band, which sees two different CO lines. So you can begin to imagine playing games with those two different lines. When they extend it, they'll have two different frequency bands. And the nice thing about that is that then you would be able to see the CO1 to 0 and the CO2 to 1 line at redshift 6 to 8 separately. And then these kind of games of cross-correlating them together could be played. But essentially, you've got two redshift windows, one at around redshift 3, one at around redshift 7. So I mentioned there was big uncertainty in the models. And so this is the kind of error bars that the sensitivity they hope to get on the power spectrum. And you can see a number of different theory models for where they might get to. You can see the baryon acoustic oscillations there. So this is the kind of clustering scales at redshift about 3. And so maybe you could start to detect the power spectrum with this. And that's sort of after 5 years of integration. But this upper limit here is from 1 year. So some of this is operating. Yeah, jump over that. So this is exciting. Within 5 years, if you can understand the systematics, you might start to get towards a detection. If you're ambitious and want to go to higher redshift, then you need a bigger instrument. And so their extension has these kind of 4 different dishes, adds in an extra receiver, and then these are the kind of forecasting for how well you can see it things. So depending upon whether this is the correct model for gas in galaxies or the dotted line is the correct model, then you get either these blue constraints or these red constraints. And you can see that with this more kind of optimistic model, then you could nicely measure the CO gas abundance going out to redshift 8. And you get a nice detection of the intensity map at these high redshifts. But if you live in a universe where this dotted, more pessimistic model is the case, then you really struggle to go beyond a redshift of 5 or so. So this is the sort of the challenge with these experiments. They're stepping into new territory as far as understanding the gas in galaxies go. I mentioned Sphere X, and that's cool because it launched earlier this year. I don't know if you were following that, but it was one of these things where there was a published launch date, it got delayed, and it got delayed, and it got delayed, and then it got delayed, and then it launched perfectly. And so this is just a little picture of how it looks. Sphere X will do lots of science. The main thing that it's going to do is a spectroscopic galaxy survey. to do cosmology. It'll also study things like the atmospheres of planets, ices, stuff like that, I think. For intensity mapping, it's nice because once you're outside of the atmosphere, you can look at H alpha, Lyman alpha, and other things. Yep, that's cool. That's cool. And so I just wanted to show this kind of nice picture from a paper by Cheng et al. So if you look at your different frequency channels for your instrument, so you've got that kind of resolution, you cross-correlate them together, what you'll see in that covariance matrix are these kind of lines where you're cross-correlating two different lines from the same redshift together. And so this sort of structure in your covariance matrix is the sort of thing that you could use to pick out the signal from particular redshifts. And so this kind of multi-tracer approach is being developed in nice frameworks. And certainly at low redshift, it offers the hope of pinning down the star formation rate very, very nicely over a kind of an interesting range of redshift. And then I also wanted to mention CCAT. So this is like an artist's impression of CCAT. This is going to see first light next year. And it's a funny telescope in that they built it in Germany, and then they disassembled it, and they're currently reassembling it in China. So that's good, because you know that hopefully, like a Lego kit, it will all fit together in the right way. But, so this has 4 different bands. Again, it observes CO and C2 over a range of different redshifts. And the idea here is to have a very deep field of about 10 square degrees. And through that, you can map out the molecular gas very precisely. So that's these little blue experimental things there. So one of the things I wanted to point out here is, so these are the different bands and the different line contributions. And this dashed line is the carbon-2. So that would be nice to observe at high redshift. You can see that at low redshift, it's the brightest line. It slowly becomes dimmer relative to low redshift CO until at sort of redshift 7 to 8. This is quite buried by the other lines. So part of the challenge for this is developing these techniques to pick out one line from the others. Cool, so I'm coming to an end. So I wanted to flag up that there's a couple of numerical tools for calculating these kind of intensity maps. So Andre was telling us last week that the latest version 4 of 21 centimeter fast will do this. There's a code I mentioned before called limfast. Both of these will produce these kind of light cones of different lines, star formation rates, and so on. Other people have codes that I have neglected to include here. Sorry, Suman. Which you can use to post-process your own favorite simulation. And so, if you're interested, these sort of techniques, tools are out there. And so really the kind of the big picture here is that we'll be able to pull everything together to get a picture of all the gas. So this is a cartoon from a Scientific American article. And the idea is you've got your galaxies here. You can probe those with intensity mapping in CO, C2. They have a Lyman alpha halo around them, which you can probe with intensity mapping. Once you get beyond that, you get to the neutral IgM at high redshift. You can probe that with a 21 centimeter. There's continuum emission as well. And if you can combine maps in all of these different wavelengths, lines, that will enable you to build up a picture of exactly what's going on with the gas at very high redshift. So that's kind of the dream, as it were. Okay, so I'm over time, so I'll finish there. So really, I wanted to drive home this idea that 21 centimeter is great. I personally love it, but it's not the only line in town. There's a lot of excitement at the moment and experimental effort for intensity mapping in lots of different lines. 21 centimeter intensity mapping at post-reionization is very interesting for doing cosmology and studying the H1 distribution. So for that, things like Meerkat, Chime, SK Mid coming soon will be very exciting. Other lines that are particularly interesting are CO and C2. And with those, you can trace molecular gas, the star formation rate out to higher redshift. So you can do a lot of interesting astrophysics, maybe cosmology, but that's less discussed. There's lots of uncertainty at the moment in the modeling. And different people use different approaches. I think it's still a bit unclear which are the best models, and probably until we get data, that will be unclear. But these experiments, COMAT, TIME, the Fred Young Space Synoptic Telescope, Sphere-X, these are happening now, and so will be very interesting over the next few years, next decade, I should say. There's lots of early detections and cross-correlations with galaxies, which is great, but the dream is to get these kind of autocorrelation detections. And that's really much harder and requires much stronger, much clearer understanding of calibrating the instrument and things like that. So there's a lot of work needed there. This is all very complementary to 21 centimeter EOR stuff. And many of the tools that people have been developing there have been lifted across to the intensity mapping area. So if you're interested in this, you should also be interested in intensity mapping, I would say. And so, yeah, watch this space. It's still very early days. The 21 centimeter EOR field is much more mature now. It's taken a decade to get there. The intensity mapping field, some of the instruments are better understood, but it's also still kind of in this early phase. So I will finish there. And thank you for your attention. And I'll take any questions you've got. Thanks. At the back.
So thanks for the lecture. So how fine can we make the resolution of our intensity maps without defeating their purpose? So we don't want to resolve sources, right? So if we are interested in the morphology on galaxy cluster scales, let us say, we still want really fine resolution, right? But yeah, so how fine can we make our intensity maps?
That's an interesting question. So, I mean, few of these instruments go down to scales that are, so here's the power spectrum for COMAT, let's say. So you can see this is K of 1 over here. So that's kind of megaparsec scales. That's probably the kind of smallest scale you're likely to go down to with this sort of an approach, I would say. That's my intuition. It's not something I've looked at in great detail. So it tends to be greater than megaparsec scales that you're looking at.
So let us say we are not just interested in the power spectra, but we want to make intensity map images and then look at the morphology directly in the image domain. So yeah, in that case, in your opinion, how fine can we go? Is it still something like megaparsec scales, or can we go sub megaparsec?
So at some point you transition into actually just wanting to resolve the galaxies themselves. So as you go to smaller and smaller, your shot noise will become more important because there's more variation from that. I don't have a good answer for that. Other question.
Yeah. So when we do cross matching of two catalogs, we run into problems with like chance coincidence where we map like a foreground radio emission with a background galaxy or vice versa.
Yep.
So how is cross correlation in this case different from that aspect?
I mean, fundamentally, it's not. So yes, so this is a bit slightly scary kind of a figure, isn't it? You've got the little red dots that are the targets and then this sea of blue. And when you cross match the two of them, yes, you'll pick out the red ones, but there'll be some chance coincidence between some of the blue ones as well. So it's not an absolute, panacea for the problem, but it will reduce the amount of contamination there.
So what is your reliability of your result from this? And
so that would depend very sensitively to like what redshift you're looking at, and so how many lines there are that contaminating, which frequencies, all of these kind of things. So I can't give a simple answer for that. There's nothing that stops you from stopping with two frequency maps. So you could imagine adding multiple frequency maps. So especially for CO, where you've got the multiple lines. And I'm sure you're aware people do this in other areas, don't they?
Thank you.
I think you have to press the button or?
Is it? Yeah. So will the recombination lines have any effect on the on this analysis? I mean, they are weaker, but they are numerous with almost like comb-like structure. So will there be their integrated effect will have any implication?
Sorry, I didn't.
The recombination lines?
Recombination lines.
Yeah.
So things
Will,
line.
I mean, they are weaker, but will they, the way you describe the C2 line being mixed with the different CO lines, will there be sort of similar effect from the radio recombination line when one looks at the redshifted 21 centimeter IM?
It's a good question. I forget exactly where they fall.
They are like comb-like structure everywhere. So if you look at, if you, the alpha lines are fairly strong and they are almost equispaced comb-like structure. Yeah, I mean, they go all the way to the redshifted H1 frequency ranges. So
yeah. It's a good question. I remember coming across that for 21 centimeter EOR, and there being a sense that you could work out what frequencies they were at and flag them. But so maybe that's something similar here. But it's not something I have any knowledge about. That's an interesting question.
And if I can ask one more about the COMAP project that you mentioned, which is in the prototyping stage, is that a new telescope altogether, or is a new instrument which will be on board some existing?
I think I misspoke when I said it was a new telescope. I think it is actually a receiver on the back of this 10.4 meter dish.
10 meter.
10.4. I think is how
where?
Is it in the? So two of the dishes they're going to expand in are in the Owens Valley. I imagine that's where the prototype is, but I'm not quite sure.
Okay.
So Caltech is heavily involved in that.
I see.
COMAP has already done one set of data release, kind of preliminary, the initial run data release.
Yes. Do you know where the dish was located?
I think it was in somewhere in US. Yeah.
Yeah.
So they have released some amount of data.
Yeah, I think it's probably the Owens Valley. That's certainly where they're going to have two other dishes.
Yeah, Jonathan, so this cross correlation between 21 centimeter and C2 intensity, you said that they will be complementary and there will be anti-correlation, right?
Yes.
So I was just curious. I mean, the places where you have this bright emission, they also be hosting the gas which is fueling that bright emission, right? So now if we look at the ISM physics, the molecular gas is actually coming from your atomic gas, right? So the depletion time scale is not kind of, very, it's not very fast that, you just form, you have H1 and that immediately it vanishes and converts into molecular gas, and from there. So I was a little bit puzzled because there is a time scale involved, and whether really you will see a anti-correlation between them, right?
Yeah, so where did I put that?
Yeah,
so yeah, it is a true statement that.
Yeah.
So if we're looking at these galaxies, it is a true statement that there will be neutral atomic hydrogen in those galaxies,
right,
which will have some 21 centimeter emission of its own.
Yes.
So with the kind of the beams that we're talking about for the EOR signal, a lot of that gets diluted away. And so what you're seeing is the neutral hydrogen in the intergalactic medium. So you're just not very sensitive to that atomic hydrogen there. Whereas for these kind of experiments, you're picking up the intensity from the molecular gas more. Does that answer the question?
Yeah, I mean, I get some of the sense, but yeah. So, I mean, what I'm saying is that, I mean, when you are getting, so the intensity map is coming from the C2 line, right?
Sure.
Right?
Let's say that I think when we made this was actually CO, but it will be
CO, okay, fine. CO
is C2.
it's basically molecular gas, right? And here, this gap, you are saying that it is because of the ionization coming from the star formation activity, which is happening in the CO heavy places, basically.
So the intensity map there is simply coming from the fact that that's a region of space where there are lots of galaxies.
Correct.
And so there's molecular gas in that
Correct.
region.
Correct.
And then the hole here is coming from the fact that because there are galaxies in this region, those galaxies are emitting ionizing photons, which have ionized the intergalactic medium around.
Right. I mean, yeah. So, but to have that CO, you must have also atomic hydrogen also, right? Now, this hole you will see if the scale is really larger,
Yes.
and in that first map, if the scales are smaller, you will actually pick up the CO.
That's right.
Right?
That's right.
Yeah. So I mean, I was just curious that, I mean, I thought that even in the normal galaxy physics and low redshift, if you see the Kenniket-Smith law, it tells like wherever more gas you have, more star formation is there, right? So I would expect that, I mean, yes, the radiation coming from those galaxies will ionize the region, but at the same time, there would be probably some amount of H1 which will give emission, right? So not completely whole kind of things. So
Yes.
right.
Yes. I mean, I don't disagree with anything that you said. I think when when you're using these kind of 10 arc minute beams here,
I agree.
then-
Yeah. So if
then that-
if it's really probing the IgM in a large, then yes. I mean,
Yeah.
but one has to see that, what would be the ratio and how much, emission.
Yeah, and I mean, there are some papers in the EOR 21 centimeter side where people have investigated including the effect of the neutral hydrogen inside
I
of
see.
galaxies.
I see.
And it modifies the details a little bit,
Right.
but it doesn't change the overall picture.
I see. Okay. Okay. Thank you.
And the holes will also evolve with time. So that's a single snapshot. Whereas that thing is not going to evolve that much in time. So you will see a varied anti-correlation. I think
That's
Okay,
also true.
That is true.
another way of
That is also true. Yeah.
doing the same thing.
Yeah, and as you go to like the post-reionization phase, that anti-correlation will become a correlation because now it's only the atomic.
Yeah. So
galaxies that-
yeah, I agree. So there is a time scale involved. Like, I mean, going from gas phase to star phase, and then for creating photon. So that one has to look at it.
Absolutely. Any other questions?
Any other questions? It's a
Yeah, hello. Very nice talk. So I was just wondering, whenever we quote a power spectrum coming from cross correlation kind of thing, let's say we are cross correlating CO and H1 power spectrum. In that case, there is always this ambiguity whether both these lines are actually like tracing the same underlying distribution identically. So, this sort of introduces a bias in the power spectrum, right? Like I might be not sure. So, how are we sort of, quantifying this bias? Maybe through some other experiments, or how do we actually quantify it?
That's a good question. Yeah, I mean, so it's certainly the case that when you model these things, you'll pick up sort of degeneracies that you can't pick out from the signal. So that's some sort of ambiguity in the cross correlation as to whether they've got different biases relative to the underlying density field or something more complicated than that. And so, I mean, it's the sort of thing that you for the interpretation side, simply have to feed that into your models, and maybe you can't get rid of it, or maybe you can constrain it. Yeah, it's I mean, when so this is, I mean, sort of one of those examples that when you do the 21 centimeter galaxy cross correlation, you'd like to be measuring just the omega H1 times the bias of the H1. But there's an extra unknown quantity in there, which is describing the degree of correlation between the two fields, and you're stuck with it. Yeah. Yeah. So, I mean, in this case, I mean, how would you break that degeneracy? Well, maybe you could use the redshift space distortions to pick out the bias. Maybe if you've got a nice model of the H1 distribution, then, and you extend this to smaller scales from the shot noise term, you can learn something about the ingredients of your halo modeling. That might be helped to break that as well. But I think you need extra information, either from the theory or the observational side. Yeah, it's annoying.
So in one of the slides where you were showing the link between star formation and CO luminosity, you said they might be correlated, but is it not well established that the CO luminosity will be linked with the amount of molecular gas and so the CO luminosity will be linked with the star formation rate?
It is well established up to a point. Yes. I simply said that just because it's not always a nice simple linear relationship between them, and if you go to different mass halos, that relationship can change a bit. So I was being a bit cavalier in what I said, but yes, up to a point it is very well established that there's a connection. I'll be around tomorrow. I can answer questions somewhere else if we want to.
Okay. So if there are no more questions right now, let us thank Jonathan again. And yeah, he's around.